homework's due on Monday. The Friday thing is that the class is online. Maybe that's why I had it confused in my mind. Any questions about the announcements or schedule-related stuff in general? No? Okay. So we're going to continue talking about suspended growth secondary treatment today, and then on Friday we'll begin fixed growth secondary treatment, talking about trickling filters. So today we'll talk about a couple of different reactor type configurations that can be beneficial in nutrient removal, and then ways to quantify the amount of sludge that gets produced in wastewater treatment, because it's a little bit different than the way we calculate sludge production in drinking water treatment. And then we'll also talk about how much oxygen needs to be delivered in an aeration basin. Now, just to review some of these terms that we may have covered before in a tangential way, bulking sludge is sludge that settles poorly, and it's important in secondary treatment that we're able to recirculate a portion of the sludge that settles. And so, although you may not think that it's going to have an influence directly on the BOD removal in the aeration basin, there is an indirect effect that if you can't settle the sludge well, then you're not able to collect it to recirculate. So bulking sludge is a problem that actually can affect the BOD removal, and it's not just an issue of convenience or variability of the clarifier performance. Of course, we've talked about the mixed liquor suspended solids and how that's the biologically active portion of the suspended solids that are being recirculated, and it's the cells that enable the waste to be broken down much more quickly in the aeration basin. And one of the ways that we are able to control the type of microorganisms that are going to thrive in the aeration basin is by how much food we load relative to the mass of microbe life inside of that reactor. And so it's not easy to directly measure how much food there is and the number of organisms there are, but we can use the BOD of the waste that's coming into the aeration as an approximation for how much substrate is there for the microbes to consume. And what we usually use is BOD5, which simply is a jar test that says how much oxygen demand is there over the course of a 5-day period. And as you'll see today when we talk about the oxygen demand in the aeration basin, the 5-day test of BOD actually doesn't tell you all of the oxygen demand that there could be. That the microbes are going to need more oxygen than they would use in a 5-day bottle test. And so we have to be aware of the fact that that 5-day bottle test isn't the entirety of the amount of oxygen that's really used. There's something called the ultimate BOD, which is if you gave the microorganisms an unlimited amount of time, how much oxygen would they demand to break down the waste? And we don't often use ultimate BOD in monitoring the performance of a wastewater treatment plant because it would take maybe a month to determine what was the oxygen that was demanded. And 5 days is long enough to wait. So just a word that when we say we've measured the BOD, the secondary question is, over what time period did you measure the BOD? So we'll return to that topic a little bit later today. And in the F to M ratio, what we are using as the approximation for how many microbes there is the variable X that we were working with last time, the concentration of suspended solids in the mixed liquor. Of course, some of them are going to be inert suspended solids, but by far the majority of those are going to be suspended solids that aren't inert, they're organic. Now it's going to be a mixture of live organisms and dead organisms, but most of the mass is live organisms, and especially if you're wasting a portion of the sludge, the dead organisms really become food for things that are still in the wastewater. So at one end of the spectrum of how heavily we favor either the food or the microorganisms is if you have a very low F to M ratio, then that means that you are having a little bit of food for a lot of microorganisms. And the advantage of that is that the microorganisms are going to be breaking down every speck of the food that they can find. And the predator microorganisms are going to be consuming the prey microorganisms. The disadvantage of an extended aeration basin is that the volume has to be larger than if you have high rate aeration. In high rate aeration, you're loading lots of food, and so the microorganisms that set up are the simpler ones, the prey rather than the predators, and smaller tanks are required, and you typically can't have the same removal of BOD in high rate aeration, but it's more space efficient. It's more energy efficient because you're using less oxygen during the period of treatment. Now theta sub c, remember, is talking about how long the average cell particle stays in this loop. It's a recirculating loop between the secondary clarifier and the aeration basin. And there's two different detention times. There's the hydraulic detention time, so it's the water molecule, how long does it spend in secondary treatment, and that's independent from the mean cell residence time, which is how long the average microbe spends in that circular loop, because it's being settled to the bottom of the secondary clarifier and recirculated. So if you have a long mean cell residence time, then you have less waste sludge because the particles of organic material are being broken down by other microorganisms that are lower on the trophic scale. You have more complete removal of BOD, and you can also have improved removal of nitrogen from the wastewater. So this figure shows that based on the temperature of the basin and how long the solids retention time, there's a certain zone that you can expect nitrification to occur. And so if you're going to have really cold temperatures in your aeration basin, then it takes a lot of time to have the microorganisms that are capable of breaking down ammonia and the ammonium ion into nitrate. Whereas if you have warmer temperatures, the microbes are more biologically active at warmer temperatures, and so the required solids retention time for nitrification is much less. Ironically, there are a handful of cases where there may be a limitation of either not enough nitrogen or not enough phosphorus in a wastewater treatment plant, where you're trying to remove one, but the other is a limiting factor. And so occasionally they'll have to add external nutrients into the aeration basin, and occasionally even BOD will be the limiting factor. And it's kind of interesting, there are a handful of wastewater treatment plants that keep bags of dog food on hand, and they'll just pour dog food into the aeration basin because that's the BOD that's required. If they've got more nitrogen and phosphorus than food available, they have to feed the microorganisms that are breaking down, that are consuming the nutrients. That isn't really common, that external nutrients have to be added or that dog food is added to the wastewater treatment plant, but it's not unheard of, and it may be a seasonal variability thing. It may be that during certain parts of the year, over the course of many decades of operation, they've come to know that they have to feed their population of microbes one thing or the other as the waste characteristics change and as the kinetics change of the reactor. Because, for instance, in Huntington, it may be that in the summertime the waste water is 20 degrees, and in the winter time when the wastewater is exposed to the elements, that it's much, much cooler. The water that comes in from the sewer doesn't vary a lot. The water that's in the sewer varies less, but because we're injecting air into the aeration basin, it's air that's taken from the outside environment, and so it's the air that's being injected into the aeration basin is the same temperature as the outside air. And so if you've got 10 degrees Fahrenheit and you're putting a lot of that air into the water, then it can cool off the water pretty quickly, even if the water came into the treatment plant at 58 degrees. One thing that you have to be careful with in the case of sewage is that metals can accumulate, and especially when you have a combined sewer that's receiving water that comes off of the street. You know, maybe if it's just a pure domestic wastewater, there is less likely to be metals like cadmium, mercury, lead. But when roadways have pollution from vehicles and from nearby industries, the combined sewers that go to the treatment plant can have metals, and through the process of settling the sludge and concentrating and thickening the sludge and excluding water, then those toxic metals can accumulate and be dangerous. So I've talked before that there's different things that you can do to tweak suspended growth systems into taking up BOD at a faster rate or taking up nutrients more than they ordinarily would. And the most common, I guess I should draw this on the board, the most common activated sludge configuration would be that the wastewater comes in from the primary clarifier. So here's our primary clarifier. There's sludge that goes off the bottom of the primary clarifier, and then the water that comes off the top of the primary clarifier is going to our aeration basin. And so we've got a little air stone at the bottom that's setting off bubbles, and it's completely mixed. So the most common configuration of an aeration basin is just that it's completely mixed. The sludge that comes off the bottom goes to a clarifier. No. Since it's completely mixed, excuse me, everything that comes out of there goes to the clarifier, and a portion of the sludge is reintroduced, whereas the water that comes off the secondary clarifier goes to disinfection. Now, in the case of plug flow, what they're doing is they're introducing the waste at one end of a rectangular reactor, and the BOD is decreasing in the direction of flow. In this typical configuration where everything's just mixed together, the concentration of substrate is the same everywhere, which biological reactions happen at a rate that's proportional to the amount of food that's present. So what I'm saying there is, if there's a lot of food, the bugs are breaking down the food more quickly. That's first order kinetics. But as you decrease the food supply, the rate of the reaction decreases. And what we want the bugs to do is we want them to break down the food as quickly as possible, because the quicker they work, the less the volume of the reactor required is. If they work slowly, we need a big reactor because we have to hold them in the reactor for a long time. But if the bugs break down the food very quickly, we don't have to have as large a reactor, we don't have to apply as much air to there, and it costs money to provide air to the aeration basin. So a disadvantage of complete mix is just that the concentration of the waste is relatively low, because you've got the waste coming in and it's instantaneously mixed with the concentration of waste that you've got at your outflow. So if you've got, let's say in our example that we worked on Monday, we wanted the discharge to be, I think it was 14.75 milligrams per liter, right? That's what we wanted our BOD to be once it comes out of the reactor. If that's the concentration you want coming out of the reactor, everything in here is 14.75 milligrams per liter. That's a complete mixed reactor. In contrast to that, in a plug flow reactor, the waste comes in at a much higher concentration. So the water that's just barely entering the reactor is at maybe 120 milligrams per liter. And so the reaction is happening very quickly at first. And then by the time you get to the end of the reactor, the concentration of BOD is down to 14.75 or whatever your discharge standard is. And the reaction is slower, but plug flow kinetics are more favorable than a completely mixed flow reactor. So that is why it would be advantageous is on a per unit volume basis, plug flow reactors are more efficient at removing BOD than a completely mixed flow reactor. Sometimes these are called completely mixed flow reactor. You may also hear them referred to as continuously stirred tank reactor, CSTR, CMFR. It means the same thing. It just means everything in there is blended and at the same concentration. So does that make sense? Does anybody have any questions about that? Okay. In this configuration, you could either put air at the same rate along the bottom, or you could reduce your air along the bottom, because at the beginning you need more air since the rate of the reaction is faster. So just to save a little bit on aeration, you could have, as the concentration of BOD decreases, you could also decrease the rate of air that's being supplied. In the case of step feed reaction, where water is coming in, this is plug flow, but step feed, the idea here is simply that you would potentially, by having the food decrease and then go back up again, decrease and then go back up again, you could nurture a different type of ecosystem than if you just had a single plug flow reaction. And you could step feed both the wastewater and the oxygen and have periods of anaerobic activity that are more advantageous for removing nutrients. We've talked a little bit about how you can adjust the F to M ratio and achieve different objectives with that, like less sludge volume by having a low F to M ratio, or having faster reactor performance with a high F to M ratio. So modified aeration is where you have a high F to M ratio. Extended aeration is where you would have low organic loading, means less food to high microorganisms. And then the amount of plug flow performance, like how closely the reactor mimics like perfect plug flow performance, because remember, no reactor is going to get there all the way. We have to add in baffles, and we talked about this earlier in the semester. The way that you can nurture plug flow reactor performance is by having diffusing baffles that kind of make the water spread out in all directions rather than just having short circuiting between two pipes connected to a tank. So our book has a series of figures that illustrates kind of newer techniques for suspended growth, and a sequencing batch reactor, this one at the top, is one where you have one tank that you would fill. You'd have a period of time, and by the way, you'd need to have several tanks in a sequencing batch reactor to provide for continuous treatment. You'd maybe have 5 tanks. At any given time, one of the tanks is filling, one of the tanks is having a reaction period where you're supplying air and the BOD is decreasing, and then another one of the tanks at this particular time is going through a period where they've stopped aerating it and it's settling, the sludge is settling down to the bottom, and then another period where you're decanting it, meaning that you're taking the water off the top of the settling basin and simultaneously settling the removing the sludge off the bottom. And so a sequencing batch reactor just says batch reactors are even more efficient than plug flow reactors. And so if you don't mind having several different of these tanks operating in a sequence of drain, fill, reaction type operations, then you can get even more efficient performance in a sequencing batch reactor. One of the ways that you can simulate plug flow reactors is by having a series of connected, continuously stirred tank reactors. And so here you can see you've just got a bunch of stirred tank reactors together, gets you closer to plug flow reactor performance, because here in the first stage the concentration is high, in the second stage the concentration is a little bit lower, but you don't have to worry quite so much about putting in a series of baffles, and typically having 4 separated CSTRs like this gets you pretty close to ideal performance that you'd see in a plug flow reactor. And then there are other types of reactor configurations where you're trying to, maybe with the use of a membrane, concentrate the sludge even more than you'd be able to with a clarifier. getting a much higher concentration of mixed liquor suspended solids so that you don't have to recirculate quite so much. And so using different stabilization tanks to condition the sludge, where inside of a stabilization tank you might intentionally starve the microbes of oxygen for a period of time so that when they get into the contact tank, when they've been starved of oxygen, they're typically likely to take up a much higher rate of phosphorus or nitrogen. And so the idea of stabilization is it's kind of sludge conditioning prior to the phase where the sludge is being aerated in the wastewater that's being treated. Sludge volume index we briefly touched on when we were talking about settling performance earlier in the semester, and it's a way for type 3 settling to characterize how well the sludge is able to settle. And remember, the three different types of settling. Type 1 assumes that you've got spherical particles that don't interact with each other as they're settling downward, and Stokes' equation is used to model type 1 settling. Type 2 settling is flocculated settling, where as the particles are settling downward, they may collide, become larger, and settle even faster. So type 3 settling is that the particles are interfering with each other. Rather than settling faster because of interaction with particles, the particles are slowing down as they get closer to the bottom, because the sludge blanket at the bottom of the clarifier is impeding the settling of particles, because there's just kind of like a layer of material at the bottom that doesn't allow the sludge to settle as quickly as it ordinarily would. So what you're doing in calculating the sludge volume index is you're just seeing how quickly that sludge blanket can allow water to pass through it and how quickly the sludge blanket can compress. So it's very different from particulate settling. And I think in that earlier portion we talked about how an SVI, sludge volume index, of between 80 to 50 is kind of in the sweet spot of, in a 30-minute period, the volume that's occupied per gram of sludge. So that test is just that you would take a portion of the water out of the aeration basin and see during a 30-minute period, which is, I mean, approximately in the range of what you could use in a secondary clarifier. The hydraulic detention time in a secondary clarifier could be in the neighborhood of 30 minutes, and so then that would tell you what the sludge concentration is likely to be that you're returning to the aeration basin. Okay, so the two things we're going to calculate today in the examples is how much air is needed and how much waste sludge is being produced for the BOD that gets removed. So how much air we have to provide is in part related to how much BOD is being broken down. Now, BOD means oxygen demand, biochemical oxygen demand, but you know, the microbes in the aeration basin are demanding oxygen, and we're going to provide it to them so that they don't get it from the river that all of this wastewater is going to. If we can provide it in the treatment plant, then we avoid the problems that come from those microbes breaking down the waste in a natural environment. So we're doing it instead in this artificial environment. So we want to quantify how much oxygen we have to supply, and then also how much sludge is being produced. And this is really different from the sludge production calculations we did with like alum and ferric chloride. You may remember that we did some sludge production calculations when we were talking about coagulation flocculation, and there it was partly related to the reduction in suspended solids and the amount of coagulant used, and if there are any like secondary conditioning agents that get added, like polymers or clay or anything. But here, in the case of wastewater treatment, the amount of sludge that's produced in part depends on the BOD that's being consumed, but also it depends on the microbes' life cycle, because the microbes are breaking down each other as well. And so we have to take into account the rate of death of the microbes as well as the amount of BOD that's being consumed. So last time in class I told you about this parameter yield, and we used it in the calculations of the example on Monday. The variable y And the table of parameters that we had said the typical yield is that for every kilogram of mixed liquor, for every kilogram of BOD that's removed, there's between 0.4 kilogram and 0.6 kilograms of mixed liquor volatile suspended solids that grows. So it's basically, you know, for how much food we give to the microbes, how much weight do they put on? And so if they're taking a kilogram of BOD out of the water, that's their substrate, how much new mass of cellular material is it? Now the rest of the mass that isn't turned into new cellular material is what they were using for cellular respiration. So that's the energy they consumed. Just in the same way that you eat food every day, but maybe you have a stable weight. So that extra food, some of the mass is turned into the, it's the energy that you use to move around, and the microbes are the same way. So it's not just the yield, though, that affects the amount of sludge that's produced. It's also their death rate that has to be accounted for. And so when we're calculating the sludge mass that's produced in wastewater treatment, we have to take into account the observed yield. So yield is just an isolated figure that doesn't account for how long the cells spend in the reactor, and then also the kinetic rate that describes the rate of death of the microorganisms. And so microorganisms have a growth rate, they have a death rate, and also we're keeping track of how long they spend in this recycle loop of the aeration basin and the secondary clarifier. And the observed yield takes those factors into account and tells you how much actual growth of sludge there is, and not just how much growth of new mass there is. And so we're taking into account, I guess you could say, you know, if you were weighing all of the people on Earth, if you were only weighing the babies, it would seem like the weight of human flesh on Earth was increasing faster than it actually is. Because if you want to weigh all of the people and keep track of how many people, like the mass of people on Earth at any given time, you have to know the rate of new births, the rate of growth, and then also the rate that people are dying. And so that's kind of analogous to what this formula is taking into account for the observed yield. Now, this formula for P sub x is telling us the rate of sludge generation. And so you'll see it takes the observed yield into account, the flow rate of the water that's being treated, and then the difference between the incoming BOD concentration and the outgoing BOD concentration. And then because typically we'll have our concentrations in terms of milligrams per liter, then we may also need to put some sort of a units conversion at the end here if we had grams per cubic meter for the substrate concentration. Because, by the way, milligrams per liter is the same as grams per cubic meter. That's the same, because they're both by a factor of 1,000. So if you have milligrams per liter for your BOD concentration, but you want the sludge produced in terms of kilograms per day, then you would need to have this divide by 1,000 factor. So this is a relatively simple example, but it'll give us a chance to calculate observed yield and also an opportunity to calculate the sludge mass here. So let's say, for instance, that we are treating 0.15 cubic meters per second. And then what comes out of the primary clarifier, here's our primary. What's coming out of the primary clarifier has a, excuse me, a BOD of 84 milligrams per liter. And what's coming out of the secondary clarifier is 11.1 milligrams per liter. So 11.1 is coming out of the secondary clarifier. The secondary clarifier, I guess I could have just as easily as said that's the BOD concentration that comes out of the aeration basin itself, because the aeration basin BOD concentration is the same as the BOD concentration in the secondary clarifier. The secondary clarifier isn't removing any more soluble BOD. It's just a place where the sludge particles are settling to the bottom. In any case, S naught is 84, S is 11.1, and here sludge age, I wanted to present it that way. That's just another phrase that's used for theta sub C. So I've referred to that as the mean cell residence time. Another way to describe that is sludge age. That's just theta sub C. So we're going to use these same typical kinetic parameters that we've used before and calculate how much sludge mass are we going to see per day given these parameters that are in front of us. So let me pause for a second. You'll need to calculate the observed yield and then substitute all of that into the formula for P sub x. Okay, so let's take a look at the solution of this sludge production example here. So our observed yield using the 0.06 inverse days depth kinetic parameter and the sludge age of 5 days. So that means although the yield itself is 0.6, the observed yield is going to be lower, 0.4615. So that's how many kilograms of additional volatile suspended solids we'll get for every kilogram of BOD that's removed. And so then, if that's the rate of growth of new cellular mass, then we want to know how much BOD is actually being taken out of the water on a mass basis. And so we have the volumetric flow rate multiplied by the difference between the input and the output BOD, and then the units conversion between grams and kilograms. So that says it's 436 kilograms per day of VSS that's going to be the sludge mass. Now sludge is mostly water. This is just the solid part of it. So we'd have to, if we wanted to know the total mass of sludge, then, you know, if it's 1 or 2% solids, you'd maybe have to multiply this by a factor of 100 if it's 1% solids. Or if it's 2% solids, multiply this by 50, and then that gives you the mass of sludge that has to be disposed of. But this is just the mass of the solid particles that is in the sludge. Okay, so that's relatively straightforward. Any questions about that one? Okay, so I realized as soon as I opened up my examples that we didn't finish this example from Monday's class. We were working on this one. I apologize that we're just now going to get back. I think it was part E that we hadn't looked at yet. We'd already calculated the aeration basin volume that's needed, but we didn't find out what is the waste rate. So let me just review where we were on that example. We had calculated the amount of BOD, the soluble concentration of BOD, because remember BOD is in two places. BOD is dissolved in the water, and it's also particulate BOD. And this example had said that a certain fraction of the suspended solids is BOD, and a certain part of it, the suspended solids, are inert. So it said 65% of the suspended solids are BOD. So if we've got 25 milligrams per liter of suspended solids, then that means we can only afford to have 13.75 milligrams per liter of soluble BOD to meet that limit of 30 milligrams per liter. So then what we did on Monday was we calculated the mean cell residence time using solver and got 1.14 days. And then from that we calculated the hydraulic detention time was 0.026 days. And then what we did last time was we took that hydraulic detention time and the flow rate of the water that's being treated, and we calculated from that the volume of the aeration basin that's needed. And then just the final step that we didn't get to in Monday's class was calculating the rate that the sludge should be wasted. So it's this last part, part E, that we didn't get to before, the sludge waste rate. So we'd be wasting basically 205 cubic meters per day of sludge in order to achieve the mean cell residence time that we're trying to hit, the 1.15 days. The way that you get that is by how much of the settled sludge do you recirculate versus how much of it do you waste. And the more that you recirculate, the longer the mean cell residence time will be. And the less that you recirculate and how much of that fraction you waste will bring the sludge age down. Okay, sorry. So that was the example from Monday's class. We just went through the sludge production example. Now let's, with the time that's remaining, talk about aeration. You could aerate the wastewater just by physically agitating it and, you know, whipping up a big frothy foam of wastewater, and by having particle contact between the air in the atmosphere and the liquid, and then it goes back down in. So you're just kind of physically agitating the water and bringing a little bit of water particles up to the surface. They become oxygenated. They go back down in. This isn't really efficient compared to adding a diffuser, which is kind of like you've probably seen in aquariums before. There are these air stones that there's a tube connected to, and it just allows the air that's coming in to turn into tiny little bubbles. And the advantage of having a really small bubble is that there's more surface area relative to the volume of the bubble. And so the smaller the bubble, it's going to actually, the oxygen will get into the water more effectively. If you have big bubbles, then they'll just get up to the surface before the oxygen gets dissolved into the liquid. And what we want is the microorganisms are actually taking the oxygen out of the liquid. The microorganisms don't take it out of the bubble. So we have to have oxygen transfer from an air bubble into the water, and then the microorganisms take the dissolved oxygen out of the water. So these diffusers are more efficient at getting the oxygen into solution than a surface agitator would. So you can see that in an aeration basin, they may have air stones or air diffusers. It's usually a membrane, like a plastic, a piece of plastic that just has a lot of little holes in it. And then they have large fans connected to tubes that take the air down to the diffusers. In order to prevent anaerobic conditions where the waste begins to be broken down in the absence of oxygen, and you have the formation of objectionable odors, we want the DO to really not go lower than 2 milligrams per liter. We could tolerate as low as 0.5 milligram per liter, but 2 milligrams per liter is a little bit better, because if you're measuring 2 milligrams per liter in bulk, there could be isolated pockets in the corners that don't get as much mixing and don't get as much oxygen, and the DO is even lower there than in the rest of the system that is being mixed well. So that's why maybe the upper limit would be advantageous. Now this is really interesting, that for every cubic meter of wastewater, a kind of a rule of thumb is that over the course of its treatment, you're going to have to provide 8 cubic meters of air. So if you have 1 cubic meter of wastewater and the average hydraulic detention time is 3 hours, then that means you're going to have to supply for every cubic meter of your liquid that's being treated 8 cubic meters over the period that the water is in the aeration basin. So it's not all at once that you have to supply that 8 cubic meters of air, but you have to provide an excess of air compared to the mass calculations that we'll look at in just a bit. The exact demand can be calculated with this formula. This formula says how many kilograms of oxygen is required, and you can see that just like the sludge production, the kilograms of oxygen required depends on the flow rate that's being treated. It depends on the difference between the inflow and the outflow BOD concentration. Now this ratio F is related to what I was describing earlier, that the 5-day BOD isn't all of the oxygen demand that's actually there. You have to know what's the ultimate oxygen demand, and since we usually only measure the 5-day BOD, then this correction factor of dividing by the fraction F will tell you the total amount of oxygen that's required. And then we subtract out a factor that's related to the sludge production, because that reduces the amount of oxygen that's required. The amount of cellular mass that's growing decreases the amount of BOD that's used for respiration. Remember, I said that the food can go one of two places. The food is either used for the life of the microbe, or it's going into additional mass of the microbe. So the oxygen that's being consumed is mainly related to its aerobic respiration and not to the increased mass. Well, shoot, we've run out of time, so here's what I'm going to do. For this example, I'm just going to email you the PDF of this example.
Okay, so just to make sure that this example gets merged into the lecture video that's being put online, I thought I'd go over this briefly. So in this example, what we're doing is trying to figure out how much air is required when we're taking the dissolved BOD from a starting point of 84 grams per cubic meter down to a final point of 11.1 grams per meter. We have already the details about how much sludge mass is being produced each day, and then we also have an idea of the ultimate BOD, which is going to be higher than the 5-day BOD. So in this example, what we have to do, find the first of all, the ratio of the ultimate BOD to the 5-day BOD, and so you can see that the 5-day BOD only represents about 68.3% of ultimately how much oxygen is required to break down this BOD. So then putting these things into our formula to determine the mass of oxygen required, you can see here through the calculations that when accounting for the rate of sludge production, then the mass of oxygen required each day is 764 kilograms per day. Now, it's not like you can drop a kilogram of oxygen into a tank and then it's 100% absorbed. To get the oxygen into the water, you have to pump air at the bottom of the tank, and these little air bubbles diffuse upwards through the liquid, and a portion of that air is going to be dissolved into the water. And so if we were just going to assume 100% transfer, like perfect efficiency of the gas into the liquid phase, this part B of the question is just saying, well, air is 23.2% oxygen by mass, and then if we assume an air density, trying to figure out, assuming 100% transfer of the air, how much would be required. And so just accounting for the air density and the percentage of air that is oxygen, you can see that I've gone through here and done the calculations, and if we had a 100% transfer from the gas into the liquid phase, then it would be 2780 cubic meters. And that's much, much lower than the 8 cubic meters of air for every 1 cubic meter of wastewater that was suggested earlier in the lecture. In fact, that's less than 1 to 1, because in this example we're saying we're treating 12,000 cubic meters of water per day, but we only need 2,000 cubic meters of air. So obviously the difference between those two figures is just that when we put an air bubble at the bottom of the tank, the majority of the oxygen that's being introduced at the bottom of the aeration basin is going to go back into the atmosphere. That bubble will get to the surface, it'll pop, and then that air is back in the atmosphere, and so only a tiny fraction of the oxygen that was introduced at the bottom of the aeration basin is actually getting into the liquid. So that's why we have to provide so much more air volume than you might expect if you just went by the mass basis.